It must have been about 10, 11, maybe months ago, maybe almost a year. I was going through one of our history books and I realized an anniversary was coming up. An anniversary that might have slipped by, but it was very important to us. And it's very important to not only us as individuals on this planet, but to this organization. It began with Henrietta Leavitt Swan, and this is what she realized. Looking towards the constellation Cepheus, there are stars called Cepheid variables. These are huge stars. They're yellow stars, much bigger than our sun, almost sometimes up to 500 to 1,000 times the mass of our sun. And they're older than our sun. Our sun is about 4.5 billion years old. These are about anywhere from 3 to 5 billion years older than our sun. Now, these very old stars do something rather peculiar. Let's begin with the hydrogen atom, the simplest atom in the universe. Beautifully put together. It has one proton and one electron. Each one has a different charge and they balance each other out. This is the way life should be. They enjoy it this way. Everything's balanced. When we look at the universe and the gorgeous pictures we see out there, everything that is red is hydrogen gas. The majority of the universe is hydrogen. The favorite color of the universe is red. The majority of what makes up our sun is hydrogen. It is the most common gas. It was the first one created after the Big Bang. But in the pressure core of a star, atoms are rammed together. And two hydrogens get rammed together and they become somebody else. They become helium. And in that process, they give off a little tiny bit of energy. And it's what we experience as heat and light from our star. That's the byproduct of this process. So what we have is a series of events that take place in stars. They start very simple with the hydrogen. Hydrogen is forced to turn into helium. Helium turns into carbon. Carbon turns into neon. Neon turns into oxygen. Oxygen turns into silicon. Silicon turns into iron, and the process stops. Now, there are more elements in between here, and they're byproducts of this process of atoms being rammed together. Up to iron, everything's just fine. After iron, everything breaks loose. We have stars collapse. We have stars explode because they become unstable. But we're only concerned right now with the hydrogen to helium process because that's what's going on inside of Cepheid variables. Here's what's happening. Two hydrogens have been rammed together and they formed a helium atom. Here they are. They're very happy. Two neutrons in blue, two protons in red, two electrons. They're balanced. But when you get into the hot cores of these stars, electrons start to get stripped off. We call them ionized. These become doubly ionized. They lose their electrons, and this is what is left. They have a double positive charge. And when this occurs, the star becomes more opaque and incredibly hot. And as it becomes hot, it begins to swell and expand. And as it expands, it grows larger and larger and becomes more transparent and more light is released. And something else happens. Those electrons that are lost suddenly come back home. And the helium atoms start picking up an electron. They become singly ionized. And when this happens, the star appears brighter. But at the same time, it now begins to cool because it's bigger. And as it begins to cool, it collapses, it compresses. And as it compresses, it goes back to the same cycle. Up and down, up and down. And the period can be 3 to 10 days. So here we have stars in the universe beating like hearts. Boom, 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 boom. And these became the markers that led to this phenomenal discovery. Signposts. So this is what begins our journey tonight on this most remarkable discovery 100 years ago. And of course, it led to the discovery. This is Hubble's work. When he found one and the universe changed. So tonight is to celebrate Henrietta Leavitt Swan. And I asked Marcia Bartusiak to join us here tonight. I first met Marcia through her books, and some of you may have too. She is an author who's written 5 separate books on the universe. My favorite is this third one right here, Einstein's Unfinished Symphony. And in her books, she had talked about Henrietta Leavitt. And I thought, who else would be better here tonight to share with us the adventure of what was discovered, how it was discovered, and the significance in the universe today to us as these tiny little bipedal carbon-based life forms on a small blue planet hurtling through the arms of the Milky Way galaxy, looking out into the universe beyond. Marcia teaches science writing at MIT, a most interesting class, and I thought tonight this would be the person I would like to explain about Henrietta Leavitt Swan.
Okay, thank you so much, David. Thank you for coming out to help me and Harvard and the observatory celebrate a scientific paper that changed the course of 20th century astronomy. It was authored by this woman, Henrietta Leavitt, and published as a Harvard College Observatory circular on March 3rd, 1912. When David said 100 years, he meant nearly, almost, exactly 100 years ago. And what she did was provide the most important tool that allowed other astronomers to discover the modern universe that we know today. She was a gifted woman with a keen eye, and she accomplished this by noticing some of those intriguing stars that David just talked about while examining photos of the southern sky. And I'm here tonight to provide some more details behind that great accomplishment. It all starts, if I can figure out how to make my change there, it all starts with this man, Edward C. Pickering, who was director of the Harvard College Observatory at the end of the 19th century and into the 20th. And he was carrying out a formidable task that he started back in the late 1800s. He wanted to catalog each and every star in the northern sky. He wanted to gauge its color, its brightness, and if there was enough light, its spectrum. And he went on, very cleverly, with great foresight, to establish an observatory in the southern hemisphere, in Peru. This was quite an innovative accomplishment to go from the north into the south. And he wanted to continue his sweep of the celestial hemisphere and also start photographing all the stars in the southern sky. And what did that mean? That meant lots and lots and lots of photographic plates. And so can you imagine all of these photographic plates? He wanted to pick out every star, gauge its color, its brightness, its spectrum. How in the world was he going to accomplish this? Well, he had a very clever way of figuring this out. This was a time when women were starting to go to college more and more. But there was a downside to this. You had all these women with this great 4-year undergraduate baccalaureate college education. They come out with their science degree, and no one wants to use them. The scientific institutions weren't as far-seeing, and they couldn't get jobs. So Pickering very cleverly knew that this was a ready workforce for him. As he said in a report here at the Harvard Observatory, these women were capable of doing as much and as good routine work as astronomers who would receive much larger salaries. 3 or 4 times as many assistants can thus be employed, and the work done correspondingly increased for a given expenditure. Pickering was very clever. And so what happened was he ended up here at the Harvard College Observatory with what came to be known as Pickering's harem. I don't know how the women thought about that, but that was what it was jokingly known at the time. Officially, they were known as computers because this assembly line of women would take these plates and they would be sitting at their desks and they would meticulously pick out every star, gauge its position exactly, its brightness, and also its spectra. And it was done. I'm so happy to be doing this lecture right here. It all happened here, right here in this very building. And if you notice, this building is made out of brick, and that was done to protect the photos from fire. The photos were on the ground floor, and there was a dumbwaiter that they would put the photos on the dumbwaiter, and that they would then hold them up to the 3rd floor, where the women were gathered in their room assessing all of the photos. One of the best known computers, you may have heard her name before, was Annie Jump Cannon. And she is the woman who established the modern stellar classification scheme that is used today. She is the one who arranged it from the blue-white, very brilliant OB A stars through the more yellow F and G stars down to the red K and M stars. And for any of you who have taken an introductory astronomy course, you may have remembered that by the famous OB, a fine girl, kiss me. And one of Pickering's most brilliant choices to work on these photographs was Henrietta Leavitt. And there she is as a young woman. Her father had a doctorate of divinity from Andover Theological Seminary, and she grew up with 4 siblings right here in the state of Massachusetts. But when she was a teenager, the family moved to Cleveland, Ohio, and she started college at Oberlin College. But by the time she was around 20 years old in 1888, she decided to come back to Massachusetts and continue her studies at the Society for the Collegiate Instruction of Women here in Cambridge. Today, we know it as Radcliffe College. And mainly she took arts and humanities courses. But in her senior year, she took an astronomy course. And it must have been an inspiration because once she graduated, that was in 1892, she decided to stay here in Cambridge and work as an unpaid volunteer right here at the observatory. And she did that for a number of years. She was a woman who was devoted to friends and family. She was serious-minded. She was a woman, as you can see from this picture, of quiet beauty with soulful eyes. A Harvard astronomer who worked with her, Solon Bailey, said of her that for light amusements she appeared to care little, but was still possessed of a nature so full of sunshine that to her all of life became beautiful and full of meaning. It says much about her that she did maintain that good disposition even when a serious illness, right after she graduated from college, she became severely deaf. And even then, she maintained this great disposition, even under this handicap. And it's also this deafness may explain why she had this amazing ability to focus and sift through immense amounts of data. Here's what the Harvard College Observatory looked like back in that era around 1900. This hodgepodge of buildings and telescope domes. Leavitt's specialty among the computers here at the observatory during these times was stellar photometry. That is, judging the magnitude of a star on the photographic plate that she was given under study. And the way she would do this is she would work at first with the photographic negative. And when you have that night sky reversed into white now, what she was looking for was how big are the stars? How big are those dark dots? It's easier to make that assessment when you have it in reverse. That's why they did it this way. And so the larger the dark dot, the brighter the star. And they had a means of gauging from the size of the dot. They could make a judgment on the brightness of the star. But along the way, she was instructed, you know, as you're looking at these various photographs, look out for variable stars. And these, of course, are stars, as David mentioned earlier, stars that are fluctuating in brightness. And you do this by comparing photographs taken at different times. Now, she would start out with the regular photograph, the positive photographic plate taken on one date. And then she would take the same plate but negative and place them on top of one another. There we go. Now both of these plates are transparent, so as you're placing the two tops, she wants to match up all the stars on those plates. But if the stars don't match, if the two dots don't exactly match, aha, you have a candidate for a variable star, a star that changed its brightness from one time in the past to the photograph that was taken later. She did this for a while, but in 1896, she actually stopped this work. She took 2 years off and she traveled through Europe. And then she went back to Wisconsin for a while to spend some time with her father, who had moved to Wisconsin. So 6 years goes by, and by 1902, she's getting a little restless. She wants to go back to astronomy. So she writes a letter to Pickering, and she's just asking, give me some advice. How can I get back in astronomy? But Pickering knew her talents. She had proven that when she was here as an unpaid volunteer. Now she was going to get paid. He wrote back immediately and said, I'm going to offer you full employment, and I'm going to give you 30 cents an hour. Hey, she wrote back and said that was a liberal offer because she knew the other computers were getting 25 cents an hour. So she was doing good. She was very talented, and he knew it. Today, I actually worked it out. That would be about minimum wage. And that's when variable stars came back into her life. It was in the spring of 1904. And she was starting to examine plates down in Peru. They were starting to take some good looks at the small Magellanic Cloud. The plates were coming back up here to Harvard, and she was starting to look at them. And she noticed from comparing some of the plates that some of the stars were changing in brightness. She got hooked. She absolutely got hooked on trying to find these variable stars. With each new delivery from Peru, she was going back and comparing the plates to try to find some more. She got so into this endeavor that one astronomer here actually called her a variable star fiend. Well, soon she was including the large Magellanic Cloud in her searches. And here is a look at how they look. If you go down into the southern hemisphere, this is how they look up in the sky together, the small and the large Magellanic Clouds. Well, by 1907, 3 years after she started, she found a total of 1,777 variables in both of these clouds. That was an absolute record. Before then, in this sector of the sky, they knew a couple dozen. She had upped that to 1,777. Well, she dutifully reported her findings in the 1908 Annals of the Harvard College Observatory. Here it is. This was the first page of that report. It was a formidable paper. It had 22 pages, most of which were like this. Every single one. Remember, 1,777 variables, and she listed them all, giving the position on the sky along with the minimum brightness and the maximum brightness. But more intriguing, all of this data, what was most intriguing was the table, simple little table she has at the end of the paper. In the course of her painstaking examination of all of these photos of the small Magellanic Cloud, she found 16 out of those 1,777 stars that looked a little different to her. They were later identified as Cepheid variable stars. And as David mentioned, these are stars that are thousands of times more luminous than our sun. And the name, as David mentioned, comes from one of the first discovered was called Delta Cepheid in the constellation Cepheus the King. And they are stars. What's really interesting about Cepheids, they're not just variable stars. They run like clockwork. When they balloon in and out, it is with immense regularity. Some change over a matter of days, some change over weeks, some months. But they are very reliably periodic. And then upon showing us this table in her paper, she goes on to say something both very modest and very bold at the same time. She says, it is worthy of notice that the brighter variables have the longer periods. How in the world did she figure that out? You know, going through more than 1,000 variables, she found out that pattern. And you can see it here. Right there are the 3 brightest stars on her list. They have magnitudes of around 11 and 12. And they do have the longer periods, 31 days, 65 days, 127 days. And on the other hand, the shortest one on this list has a period of 1.2 days, and that's about those stars are about 2 orders of magnitude fainter. She also noticed a particular difference to the rhythm of the breathing of the star. She noticed that when they do change in brightness, it's a sharp rise to brightness and then a slow weakening to the faintness. It's smallest magnitude, or I should say it's weaker magnitude. And then they stay faint for longer than they're bright. Now, she could trust that this was actually happening. You might say, well, maybe this rule isn't happening. Maybe some of those stars are farther away than others. But she knew that she was looking at one object called the Small Magellanic Cloud, where all the stars are pretty much the same distance from Earth. So this rule was going to hold tight. The brighter the star, the slower the period. She also suspected at this time, this was in 1908, that, this might be handy. This might be handy as a measuring tool. Because she knew what she had on hand was a standard candle. If you know how bright a candle is right by you, and then you see that candle further off, by noticing how dim the candle is and knowing that it's dimming in a regular fashion by an inverse square law, then you can guess the distance. She was finding a potential standard candle because there's this link between the Cepheid's brightness and its period. So the potential was there. You see a Cepheid far in the distance. You don't know how far it is, but then you watch it blink and you count what its period is. Then if you can link that period to the brightness, its actual brightness, and then say, how far away does it have to be to get so dim that I see it now? You can make an estimate of its distance. Unfortunately, in 1908, 16 data points wasn't enough. She knew that. She knew that 16 points on a graph weren't going to help her much. She had to gather some more data. So there was a bit of a delay. 1908 was a precursor. She was starting to sense that something was there, but some other things got in the way. For one, she was chronically ill, not only deaf, but she was faced with a number of illnesses, and that took her away from her work for some time. Her father died, and she had to deal with that. And then there was this sheer astronomical problem. Cepheids are rare. You're catching them at a very rare moment in their stellar life. So finding Cepheids, I mean, she had spent years gathering those many, 1,777 stars, and only 16 of them were Cepheids. She had to wait a while, look at more photographic plates to try to find some more. 4 years it went on. She would sit at her desk there upstairs, right here in this building, and work away. This picture taken obviously on a nice day with the window open and the wind having the shade go out. In 1912, 4 more years here at her desk, she was able to find 9 more Cepheid variables. That made all the difference. Finally, she was able, with her new collection of 25 variable Cepheid stars, finally establish a mathematical relationship between a Cepheid's brightness and its period. Here is the historic graph published as a Harvard College Observatory circular, number 173, on March 3rd, 1912. On a logarithmic scale, it's a straight shot upward. As the Cepheid's brightness rises, the period gets longer. You see all those stars huddling pretty well straight on her graph. The relationship, the top line is showing the relationship when the Cepheids are at their brightest. The lower line is showing the Cepheids when their brightnesses are at the minimum. The relationship works either way, bright or dim. Well, the language that Henrietta Leavitt used in her paper shows her excitement over this, and it's quite apparent. What she said was, a remarkable relation between the brightness of these variables and the length of their periods will be noticed. Remarkable relation. This is not language usually used in a scientific paper. Scientists are usually very modest and careful in saying anything is remarkable. Well, this was remarkable, and she knew it. But there was one missing piece of information. Her graphs show this wonderful lineup of how the brightnesses change with the period. But what is missing is knowing the absolute brightness of what a Cepheid star would be if it was right next to you. At this time, astronomers could maybe measure a few hundred, several hundred light years out into the universe. They had methods called parallax. It's sort of like surveying on Earth, a triangulation process that could take you out a few several hundred light years away. But there is no Cepheid star that close to us. So she didn't have a way of knowing what's the absolute brightness of a Cepheid. She couldn't calibrate her graph. If she knew the absolute brightness of just one Cepheid, you would know all the rest from her graph. Then you really could get cooking. But alas, Henrietta could not go any further with this. There was a number of reasons. One, she couldn't go to a telescope. Women didn't go to the mountain with men to share the telescope at night. That was not considered proper. So that was out. She also had these illnesses, and her doctor actually advised her not to go to a telescope and observe. It was cold, it was damp, and it wasn't good for her health. But it was also because of Pickering. She could have done some calculations at her desk. But Pickering held the strong conviction that the mission of the Harvard College Observatory was to gather data, not to do any theoretical calculations. That was for Princeton University, not Harvard. One Harvard astronomer said that Pickering chose his computers to work, not to think. Well, ultimately, shortly after the publication of this paper, Pickering put Henrietta Leavitt onto another project. And she just said, "Aye, aye, sir," and went on to the new project, which was a classification scheme for stellar magnitudes, which did actually serve eventually as an international system. So it was very useful work, but it took her away from her beloved variable stars that she really did enjoy working on. The first man to actually make the crude calibration to try to find calibrate this period luminosity law that Henrietta Leavitt had presented the astronomy community was carried out by this man, Einar Hertzsprung, in 1914, 2 years after her paper came out. He was the one who actually first recognized that the special stars that Henrietta was noticing in her paper were indeed Cepheid variables. But the man who really put Leavitt's new tool to use was this man, Harlow Shapley. He, at the time, had recently gotten his PhD from Princeton, was now the up-and-comer at the new Mount Wilson Observatory in Southern California. And he actually made a new and improved period luminosity law using Leavitt's work as a springboard, and decided to find the distances to all the globular clusters that surround the Milky Way galaxy, at the time 69 in all. And he used her relationship to find the distances, the actual distances to those clusters. And in this way, he was able to find out that the Milky Way galaxy was far larger than people had even suspected. Back in the 1910s, it was estimated that the Milky Way galaxy extended, its width was about 10,000 light years. With these measurements, using the new period luminosity law, the measurement, this new cosmic measuring tape that she had developed, he was able to establish, he estimated, that the Milky Way was 300,000 light years long, a tremendous increase. It's since come down. We know there's been recalibration. It's now 100,000 light years wide, but still a tremendous difference from 10,000 to 100,000 light years wide. At the same time, he was noticing that most of the globular clusters were off to the side, that the center of the Milky Way was not around the Earth, but over towards the Sagittarius constellation, where most of these globular clusters were hovered. So he changed our idea that the Earth, we once thought that the Earth was the center of the Milky Way, and it wasn't. As Shapley liked to put it, the solar system is off-center and consequently man is too, which is a rather nice idea because it means that man is not such a big chicken. He is incidental. So this was one of the first the tremblers, earthquakes to start coming into early 20th century astronomy. Here we're finding out that the Earth is not the center of the Milky Way galaxy. But of course, the triumph for Leavitt's new tool was Edwin Hubble's work with the Andromeda Nebula. He used this new cosmic measuring tape to prove that a variable star that he found in the Andromeda galaxy, he first noticed it in 1923, in October 1923. He found out it was indeed a Cepheid, and that allowed him to apply this new rule and discover that Andromeda was not a nebula within the borders of the Milky Way, but indeed was far, far beyond, outside the Milky Way galaxy. In fact, we know now it's 2 million light years distance. Here was the birth, truly the birth, of the modern universe that we know today, knowing that the Milky Way is just one of billions of other galaxies in our universe, and more than that, the Cepheids were also used to prove that the universe is expanding. Who knows how longer it would have taken to prove that directly without Henrietta Leavitt's vital, vital contribution. As they say, sometimes the best man for the job isn't. Well, to close out, let's come back to the Harvard College Observatory. In 1919, Edward Pickering died. And who should replace him as director but Harlow Shapley? And as soon as he arrived in 1921, Henrietta Leavitt went to his office, sat down, and said, I want to get back to my variable star work. Unlike Pickering, Shapley was happy for her to do this because he knew he needed more data to make the period luminosity law work for him and his work. And he gave her his blessing to go back to work on the variable stars. He wished her success. Meanwhile, a few years later, in 1925, a Royal Swedish Academy of Sciences member contacted the observatory to inquire about Henrietta Leavitt's discovery. He was intending to nominate her for a Nobel Prize. That is how important her discovery was. They knew in that short a time, between 1912 and 1925, they knew how important this discovery had been and was to astronomy. Unfortunately, though, he was 4 years too late. Leavitt had passed away at the age of 53 in 1921, not too long after that visit of hers to the office of Harlow Shapley. And by the rules of the Nobel Prize, the award cannot be given to individuals who have already passed away. She had died after a long and grueling struggle with stomach cancer. And by the time of her death, she had discovered 2,400 variables, about half the number then known to exist. So all I can say is, Happy anniversary, Henrietta. Thank you.